In this tutorial, we will learn how to compute measures of central tendency like mean and median in R, as well as measures of dispersion like variance and standard deviation and interquartile range, again using R. We'll also learn how to create and visualize different distributions using the histogram function and a boxplot function as well. So to get started, we're going to be working with this data file here today, which is employee_demo as the name or the title of it. And again, that's employee_demo, and note that it's all lowercase. This is a comma separated values file or a .csv file. And I have already taken the step of saving it to a folder that I will later set as my working directory in my R session. And so here you can see I have saved it to my H drive R workshop folder here, and you can see the exact name of that data file here, and we get confirmation that it is indeed a comma separated values file. And this is important because we're going to be using the read.csv function to read it in, which reads in comma separated values files. All right, so now that we have that out of the way, we're ready to go to our RStudio session here. When we arrive, we see our console window with some information about the license and the R version. We can go ahead and clear that out by going to Edit and Clear Console. Again, that's Edit, Clear Console, or if you're using a Windows computer, it would be Control+L. All right, the next thing we're going to do is open an R script editor window so that we can write annotations, save our work, and create a script that we can then use to reproduce our session at a later date or use it to collaborate with other people. So to do so, we'll go to File, New File, R script. Again, that's File, New File, R script. So now we have our new R script editor window open. As you go along, make sure that you save regularly. You can save it using this disk icon here, or you can go to File, Save As when the R script editor window is open to save it. So I'm going to use some hashtag annotations, which means that anything that comes to the right of a hashtag on a particular line is going to be treated as an annotation and not as actual codes that R or commands that R would actually run. All right, so the first thing I'll do is just note what the purpose of this tutorial is, which is measures of central tendency and dispersion in R. And I'll also make a second line here and call this visualizing distributions using histogram and boxplot. And the reason I'm mentioning that, and the reason we're going to be visualizing and doing some data visualizations in the form of histogram and boxplots, is that this can be a really useful way of helping to understand which measures of central tendency and dispersion might be most appropriate to use in order to understand different characteristics of the variables we have. All right, so the next thing I'm going to do is, as I mentioned before, I save that employee_demo data file that we're going to be working with today to a folder, and now I need to set that folder as my working directory in this session. So I'll make a note that I'm going to set my working directory, and I'll use the setwd function from base R. And within the parentheses, as a sole parenthetical argument, I'll enter quotation marks. And within those quotation marks, I happen to know off the top of my head that I've saved that file into my H drive, and within my H drive, my R workshop folder. So I'm going to type in the exact name of that path there within the quotation marks, and then click Run when my cursor is somewhere on that line. Now, alternatively, I could have gone to Session, Set Working Directory, and Choose Directory from the drop-down menus, and I could have selected the folder where I saved that file and set the working directory that way, and then you would have seen the same code appear with the same path that's your working directory in your console, and then you can copy it and then paste it into your actual R script, which makes it easier in subsequent sessions. Now, I do want to point out that almost certainly your working directory is going to be in a different location, in a different drive than what I have here. This is just the drive and the folder that I'm working with here today. All right, so the next thing we're going to do is read in that data file that I've been alluding to and that we've already viewed. And when we do this, we'll need to come up with some kind of name for the object that we'll assign that data frame to. And so I'm going to call it just demo, D-E-M-O, because the data file we're working with is employee_demo, where the demo refers to demographics as in employee demographics. Let's just use that naming convention and call this just demo for short. And so we'll use the left-handed arrow so that we can assign what we read in using the read.csv function to an object that we're arbitrarily calling demo here. So call read.csv is the name of the function we're going to use to read in that comma-separated values or .csv file. And as the sole parenthetical argument and within quotation marks, put the exact name or type in or copy and paste in the exact name of the file. This one was pretty easy to remember. It's employee_demo, all lowercase, and make sure that you add that .csv extension here when using the read.csv function. So everything looks good here. It looks like I wrote it down without any kind of typographical errors, but do remember that the name of the file is space sensitive, so do be sure that you don't include extra spaces, and if there is a space, be sure to include it. All right, so I clicked run there. It looks like in our console we have blue font or blue text, which is usually a good sign. And the next thing we'll do is take a look at the data file we're going to be working with, or in other words, the data frame object here. It has 30 observations, which in this case, observations refers to employees. So we have 30 employees in our sample in our data file here today, and 5 variables. So let's click here on the object to view it in our viewer window here. Alternatively, you could have used the view function with a capital V and just typed in the exact name of your data frame object to call this up using that approach, or you could print it to your console. We do have 30 rows here, so sometimes it's nicer to look in the viewer window because we can do some sorting and things like that. All right, so you'll see that we have unique identifier variable, the employee ID variable here. We have a facility variable, an education variable, and a performance and age variable. And I simulated these data such that the facility variable can best be described as having a nominal measurement scale. The education variable is an ordinal measurement scale. The performance variable as an interval measurement scale, and the age variable as a ratio measurement scale. And we're going to be focusing on today the performance and age variables because they do have an interval and or a ratio measurement scale here. So the reason that we're going to be focusing on just the variables with an interval or ratio measurement scale is these tend to be most amenable to using and applying measures of central tendency like your mean, your median, as well as measures of dispersion like variance, standard deviation, range, and interquartile range because they have inherently numeric values and there is assumed to be equal intervals between different integers in these numbers. Okay. All right, so again, we'll be working with performance and age here today. And just remember that it's performance with a capital P because R is case sensitive with variable names like this, and it's age with a capital A. Okay, so commit that to memory. And the first thing that we're going to do is, as I mentioned, we're going to visualize our data. And so we will start with the histogram function. So let's start with age here today. So to use the histogram function from base R, it is just HIST or hist, all lowercase. And it's really simple to get a basic histogram going here. It'll appear in our plots window here. So I'm just opening it up so we'll get a bigger histogram here when it does open. And as our sole argument to get us started here, we're going to type in the name of our data frame, followed by the $ operator, and followed by the age variable. Okay. So, and I'll make a note above here that we are creating a histogram, okay? So a histogram is a really useful data visualization display type for visualizing and understanding the distribution of a variable, such as whether it's normally distributed for the most part, or it has a positive or a negative skew to it. Now, when it comes to displaying data as a histogram, and this is just in general, when you have more cases and observations in your sample, you're going to be more likely to see data that approximates a normal distribution. And when you have small data sets like we're working with here today, where we have just 30 observations, and specifically in this case, 30 employees, the histogram is not going to be as clear in terms, it'll look a little bit lumpy and it might be harder to see whether a normal distribution or some deviation that's meaningful from a normal distribution actually exists. But nonetheless, this should give us a rough idea whether our data would meet an assumption of univariate normality, for example. Okay, so let's go ahead and with our cursor somewhere on this line or just highlighting the whole thing, click run. And I should mention too, if you're wondering why we're using the $ operator here, the $ operator is a way of for lack of a better expression, attaching a variable to a data frame, it's saying that this age variable belongs to this data frame so that this function knows where to look for this variable. Okay, so we ran that histogram function. You can see here in our viewer window, in our plots window, that, well, it looks like we have roughly a normal distribution. And so what is a histogram? Well, a histogram is essentially just setting a series of ranges, and this function does the range size by default. And each range has a breakpoint on either side, or just simply what are called breaks. And so here you can see it's these ranges are well, in this case, 2-year increments here. And then it's the frequency of scores within each one of these ranges. So the height of the bar represents the frequency of scores, or the counts, in other words. Now, if you wanted to save this, and this would be perfectly fine for our purposes, this is a histogram. It gives you an idea of the shape of the distribution. This looks like a roughly normal distribution. So the mean and the median should probably be at about the same, value, given this is approximately a normal distribution. And if this is good enough for you, you can export it by going to the Export tab here, either saving it as an image, and specifically a PNG file, or as a PDF, or you can copy it to a clipboard here. You can copy this and then paste it to a document of your choosing, such as a PowerPoint, Word document, Google Sheets, or something like that. All right. The next thing that we're going to do is, this is completely optional, but if you're curious on how you can make this maybe a little bit more aesthetically pleasing, I'll show you some quick arguments that you can add to this to change the color, to change the breaks, and things like that. Okay, so I'll just make a note that this is optional, and I'll call this stylizing a histogram. Okay, and so what we'll do is we'll start with that same code we just wrote for the histogram function above, and again, that's hist, which is an abbreviation for histogram there. And I'll do each argument on a separate row here, a separate line. And so we start off with the first argument, just designated what the variable is and what data frame it comes from. The next thing we might want to change is, note here that it looks like the high point here in terms of the tallest point in the distribution might actually be slightly taller than the y-axis here. So if we want to adjust the y-limit, we can use the y-lim argument here for the hist function. And this is, a lot of these arguments will be similar to the bar plot function and other types of plotting functions from the base R functions that can be used to create graphics like this. And so if we do y-lim, and then we use the C function, which you can think C for combine, and this is also from base R, we can create a vector where the lowest value is going to be the low point on our y-axis, and let's just go ahead and keep that at 0. Add a comma, and then we need to specify what we want the high point to be. Let's just bump this up to, let's say 20 here. Let's bump it up to 20. All right, and watch what happens if we run this now. You'll see that we've adjusted this. Okay, so we can keep building on this. So also, this isn't a very meaningful, well, it might be meaningful for us because we know what demo refers to here and what a $sign is, but for someone who's not familiar with R or our data sets that we're working with, it might be more meaningful to them and informative if we can come up with better axis labels. So to do that, we can use the xlab argument to change the y or the x-axis label, and we do xlab equals, and then within quotation marks put whatever we want. So I'm going to say, let's call this employee age, and we can run that, verify that it works, and so you see we've updated it. Now, I'm just going to show frequency is actually fine, and from my point of view, I think that's a good way, but let's just call this count instead on the x-axis, or rather the y-axis, so we can do ylab equals for the y-axis label. So that's ylab there. And let's do within quotation marks count, okay? Just to change that a bit. So watch what happens when we update this now. Now we see the y-axis label has changed to count. Now, what else can we do here? Well, the next thing we can do is let's change the color of the bars, okay? So it's gray, which is fine, but maybe you want to change it to one of my favorite colors in that comes standard in R, which is Dodger blue. So you can write in the actual text name of that color. It's just col, C-O-L for color equals, and then put in the quotation marks, the name of a color, okay? And so here we go. And so you could keep on refining this and so forth. And you might be wondering at this point, well, how do I know what all the colors are that are available to an R? me and R. If you go down to your console, you can just type in the colors function here. So it's just COLORS, and this is from base R. And then you'll see we just leave the parentheses empty. Hit return, and you get 657 colors. So you could, let's see what slate blue 2 looks like. We can copy that, paste that in, run. So slate blue looks like this. All right. The last thing I want to show you is the breaks argument. And that refers to the points, the break points here that we have. So you can see they're at 22, 24, 26, 28, 30, 32, and 34. So in increments of 2. If we use the C function or the combine function again, we can actually set these up manually. So what I'm about to do is completely arbitrary, and it's just for the sake of illustration. But let's say we want coarser or wider bins or breaks that we have. So the rectangles are going to be wider here. And if we want to do that, we can use the C function, and I'm going to do the first breakpoint is at 20. And just make sure that the lowest breakpoint you have is equal to or lower than the lowest actual or the minimum value in your variable. And then make sure that the highest value is equal to or greater than the highest or the maximum value for the variable you're working with, or the maximum score, I should say. So I'm going to go in increments of 5 here. So let's say 30, 35, and that should actually do us there. So we're doing 20, 25, 30, 35, and let's update it here. Okay, and so you can see there, and it actually looks like we went beyond the top of the distribution since we don't see a black line there. Let's increase the Y limit max there to 30. So we can increase this from 20 to 30. Click run. Okay, there we go. So this is not very informative here, but it gives the idea how you can work with the breaks as well. You don't need to do any of these optional things, but you might, if you get into it and you want to do things more stylistically and add style, color, things like that, this is the way that you can do this using the histogram function. All right, so the next thing that we're going to do is we're going to be creating a box plot, sometimes called the box and whiskers plot, and you'll see why in just a second if you're not familiar with this. Fortunately, the name for this plot in base R is just box plot, all lowercase, and of course one word here. And so we will actually, let's go ahead and use that performance variable instead of the age variable to illustrate this, just to mix things up here. Okay, so we'll just do the name of the data frame, $ operator, and the exact name of the performance variable, which is performance with a capital P. So essentially the same type of argument we entered for the histogram function or the hist function from above. And let's just do the very basic form of a box plot by just running this function as is with that single argument. All right, so here you can see a box plot or a box and whiskers plot. So what does this represent? Well, here on the y-axis rather, these are the potential values. So this is the range of values that we see for this variable. And this is a performance variable. And if we look at the data, you can see that the actual observed values are from about 3.8 to up to 10. And let's assume that this is an interval measurement scale, because 0 for this variable just means very low levels of performance. It doesn't mean the absence of performance for these employees. And you can see that a 10 would mean, let's assume, like exceptional levels of performance here. And we're assuming equal intervals between integers for this. So this would mean that we can consider this variable to be an interval measurement scale. Whereas age we would consider to be a ratio measurement scale, because age, while it has equal intervals like the performance measure, it also has a meaningful 0 point, where because age is being measured in years here, an age of 0 years would mean the absence of years, in other words. The absence of age is another way of thinking of it, okay? And so that's why we would classify this one, age, technically as a ratio measurement scale. All right, so back to the box plot here. So how do we interpret this? So again, we've got the performance levels, our performance scores, potential values on the y-axis here. And then you see this solid, thick horizontal bar here. This is your median. This is your median performance score in this context. Okay, so what is this lower end of the box here? Okay, so the lower horizontal end in this shaded box here, this is going to be our lower quartile, or our 25th percentile is another way of saying that. The upper edge of the box, horizontal edge, is going to be the upper quartile, or 75th percentile. And the range between the upper and lower quartiles, this is our interquartile range here displayed, okay? And so then we have our whiskers. And so what do our whiskers represent? Well, it represents the variation outside of the middle 50% of our distribution. So the interquartile range does represent the middle 50% of our distribution. And if you remember, a median is the middlemost score if you were to rank order them, okay? And then if you look at the actual bars that are attached to these whiskers here, these are going to, the lower bar is going to be equal to either the lowest possible observed value, which was 3.8 that we saw earlier, or 1.5 times the interquartile range, whichever is a larger value here for when we're talking about the low end. Now for the high end here, this upper bar is going to be equal to the maximum value we observed, which was a 10. We saw a couple people got 10s on performances, or it's going to be equal to 1.5 times the interquartile range. So the distance here would be that length, and it's going to be whichever one is smaller, okay? And so what that means is if you do see a box and whiskers where you have points that are visible outside or beyond or more extreme than either one of these bars, those might be candidates by conventional standards for potential outliers that you might want to either investigate or remove depending on the circumstance, or at least be aware of. Okay, so that is how a box plot works. Just like with the histogram, you can stop right here. You don't need to move on with this box plot here. You could just export it as an image file or as a PDF, or copy it to a clipboard and just paste it into another document if that's what you want to do. Now what I'm about to do is another optional session here. So if you want to stylize this a little bit, and I'm going to point out that this is optional again, you don't need to do this for our purposes, but if you want to do optional and stylizing a box plot, here's what we're going to do. We're going to start with the code we already wrote here, and then we're going to add arguments just like we did with the hist or the histogram function from above. Okay? So using commas, we're separating our arguments from each other. Well, right here we can adjust the y limit if we'd like. So in this case, we do know that theoretically that this performance scale, or at least this is what I'm telling you, let's say it can range from 0 to 10, okay? And so in that case, let's go ahead and use the ylim argument, same one as we did before with the hist function up there. We'll use the c function again. Let's set the lower end of the y-axis limit to 0, whereas right now it's at about, it looks like it's about 3.7, 3.8 or something. And let's set the upper end, let's just keep that at 10 because we know that's the max score that is observed and the max score that's possible. So let's update this. Okay, that looks a little bit better because at least it gives us a better idea of where these scores fall in the realm of possible scores. Okay, so you see that really no one was getting super low scores in terms of their performance scores or job performance scores among this sample of 30 employees here. Okay, another thing that we can do is we can remove the, if we'd like, we can actually remove, or not rather remove, we can change the color here by using the same call argument we saw above with the hist function, and simply enter a color here. I'm just going to do simple orange that comes standard with R. Click run. And you can see we've updated it. You could export it if you wanted. Now this is all making me remember. Let's go back really quickly to the stylized histogram we were creating. Click run. One thing I forgot to mention is that you can change the main title here too. And the way that you do that is by, let's add another argument to the stylized histogram function up here. And if you just use the main argument, main, you can change the title. If you put something in quotation marks, like I'll just do a test right here and click run, it changes that to whatever you change it to in the quotation marks. I'm going to put the null operator here, and that's capital N-U-L-L, all caps, because I don't want any kind of title for this. So that's how you could, if you do have a main title on one of these plots, that's how you can remove it using the main equals argument and setting main equals to N-U-L-L. All right, so now we are ready to compute measures of central tendency. Unfortunately, all these functions we're going to be working with here to do central tendency and dispersion, they are pretty intuitively named, and that makes them easier to remember, hopefully. But these are a lot of things to remember, and I often recommend having some kind of code book or code example library that you can refer to, because it'd be unrealistic to remember every single code and strange naming conventions of different functions and things like that, especially arguments within functions. Okay, so let's start out with those measures of central tendency. And let's start with the mean function, and let's do the mean of age. Okay, so it's fortunately the mean or the average is MEAN, all lowercase, and we will just copy and paste this from above to make it quick. So it's just demo, $, and the name of the variable here. So the name of the data frame, $, operator, name of the variable. And we don't have any missing data, but it's good to get in the habit of, in my opinion, of doing this, which is using the na.rm argument and setting this to true. And this just stands for remove missing data true before running this. And so this way you don't get an error message or something like that if you were to have any missing values in the variable that you're trying to compute one of these measures of central tendency for. So we can click run there. We can see that the mean for age is 28. Okay, so that's the average age that we see. And because this is a relatively normal distribution, that should be at about the center of that distribution, and the median should be about the same. So let's check. We're going to copy this and paste it below. And now for most of the remaining functions, we're just going to be switching out the name of the functions, but keeping these two arguments exactly the same. So let's do the median function next. Okay, it's just MEDIAN, all lowercase, click run. Well, the median is exactly the same. It's 28 years as well. So we do see the mean and the median being exactly the same, which gives us further evidence that this is a pretty normal distribution that we're talking about right here. Okay, so what do we do now? Well, let's compute some measures of dispersion, sometimes called measures of variation. Okay, so let's talk about the spread of our scores and how much they vary. So the first one that we'll do is mainly out of convention, although we don't typically interpret this one, and I'll just paste an example code here because we're just going to switch out the mean with var, and VAR, all lowercase, stands for variance. If we run this with the same two arguments as above, we get a variance of 7.10. Okay, well, that's not super meaningful. And the reason for that is that it's not a standardized metric here. So one way we could get to a standard deviation, for example, and I'll actually, let me make some notes here just so that it's completely clear. Making some hashtag annotations. Again, anything I put to the right to the annotation on a line won't be treated as a command for R. And let's say this is variance here. Now, to do standard deviation, we could, if we wanted to do this in a more cumbersome way, we could copy the variance here. Use the sqrt square root function and wrap that around what we did for the variance function there, and click run. And we see we get a square root of like 2.67 or so. Okay. Now, this is one way to estimate the standard deviation here. And the best way is going to be to just use the SD function. So I'm just going to copy the variance here, that whole line there, and paste it here, and just replace var with SD. That's SD lowercase for standard deviation. Same arguments within, and I'll just note, best way to estimate the standard deviation. Click run, and you'll see it's exactly the same. So that's how we can get there. I'm actually going to delete this just so that it doesn't get confusing here, and we'll just use the conventional functions there. So standard deviation. All right, so what about some other useful measures of dispersion? Actually, and let's take this moment, since typically when we report the mean and the mean, we typically report the standard deviation with it. So how do we interpret this? Well, if the mean is 28 years, okay, and the standard deviation of is 2.67 about, well, then what does that mean? Well, it means that if we're talking about 68% of people's ages will fall within 2.67 or one standard deviation above and below the mean of 28 years. Okay, So again, that's about approximately 68% of people's ages or scores more generally will fall between one plus or minus one standard deviation of the mean of 28 years, and that standard deviation happens to be 2.67 here. Okay. Now, if we were to talk about where 95% of those scores fall in the distribution, 95% of the ages fall between plus or minus 2 standard deviations of 28. And so what is 2 standard deviations here? Well, we can just multiply 2 times the standard deviation and click run here. It's about 5.33, okay? So that means that 95% of people fall between, so 28 minus about 22 point something, 22.6 or so years of age, and let's say 33.33 years of age or so, okay? So that's where 95%, and that's just, again, plus or minus 1 standard deviation. That's going to represent around the mean is going to be 68% of the people included within that range, and plus or minus 2 standard deviations around the mean, that is plus or minus 95% of observations or scores will fall in there. All right, so that's how we can interpret that. The next thing that we'll do is I'll show you how to do the min and the max. So if you want to compute the min, the minimum score, use the min function, min, all lowercase, same arguments as above, click run. So the minimum age here is 22 years. We copy this, paste it below. To get the maximum score for the variable that was observed, just do max, all lowercase for max, and click run. And we see it's 34 years. So the lowest observed age in this case is 22 years. The highest observed age is 34 years. So I'll make notes here that this is the minimum score, and this is the maximum score. All right, so next what we'll do is we'll do the range function and just copy and paste in the exact same 2 arguments we've been using thus far. So just paste it in here. And note that this is the range of scores. And so this will give us actually the min and the max in a single function if we prefer to do it that way. So here you can see we've got the same min, 22 years, and the same max, 34 years. So now we're ready for the IQR, or the interquartile range. And it's going to use the exact same 2 functions we've been using so far. So you can just copy and paste those directly in. And it's IQR, and it's important to note this is all uppercase letters here. So this is all capitalized, capital I, capital Q, capital R. And this is the interquartile range, or IQR. And so the interquartile range is 3. So let's actually scroll back to our box plot here. So the interquartile range is 3 years, which is the distance between here the upper quartile and the lower quartile, or between or in other words, the distance between the 75th percentile and the 25th percentile. So this is 3 years right here. The orange vertical space represents 3 years. Now, sometimes it's more useful to actually, or not more useful, but it's also useful to estimate the actual 25th percentile and 75th percentile values, or in other words, the lower quartile and the upper quartile values. And to do so, we'll use a function called the Quantile function. And I'm setting this aside a little bit because it uses different argument structure than what we've been using thus far. Okay, so to do the Quantile function, we are going to use the same first argument, which is the name of the data frame object, $, and the name of the variable we wish to estimate the quantile for in terms of the distribution of scores. As the second argument, though, we are going to enter whatever percentile we want to estimate. So if we want to estimate the lower quartile, that would be the 25th percentile. So we just put in the proportion 0.25. 0.25 here. You can put any proportion you want in here and click run. And so we get the 25th percentile of scores is 27 years here. In other words, this is the lower quartile, or the 25th percentile, same thing. Now to get the upper quartile, I'm just going to copy and paste that same code below. I'm just going to change this proportion from 0.25 to 0.75. And this is going to represent the 75th percentile or the upper quartile. So it's the value, this top value now. Before the lower quartile is here, upper quartile here. Let's click run. And as you can see, if you take, this is 30 years. If you take 30 minus 7, so upper quartile minus lower quartile value, you get 3, which is our interquartile range. Okay. And so typically the interquartile range and the lower and upper quartiles are reported in addition to the median when you're reporting that. And this makes a lot of sense here because this is what you see in a box plot here. All those values are represented visually here. And so you would say that the median is the middlemost score, and then you could say that the middle 50% of scores fall within 3 years here. And which 3 years do those middle 50% of scores fall? And that represents the interquartile range. Well, they fall between 27 years and 30 years. So 27 and 30. And I guess I've been referring here to, this is actually our performance box plot here. So let me update this to age here. So we're referencing the same thing. Okay, so this is the age box plot here. And actually you can see with age, there's a little bit of an outlier down here at 22 years. And so what you'll see is this is the, so this looks more appropriate here. This is the upper quartile is 30 years, which we see. So that's 75th percentile. The lower quartile is 27 years, which you see represented visually here. The median here is 28. And then we have the whiskers as well. All right, and because we have this value here below the lower whisker, it's more extreme. It means we might treat this as an outlier. So that person that's 22 years old in our sample, you could potentially say that they are an outlier, or at least you might look into it more, make sure that's a correct value for them or correct age. All right, so I'll delete this here. And now we have estimated or computed measures of dispersion and central tendency using some base R functions. And we also created a box plot using the Boxplot function from base R. And we used the histogram function, or the hist function, to create a histogram as well. So this wraps up this tutorial on measures of central tendency and dispersion in R and how to visualize distributions using the histogram and Boxplot functions.